Hello and welcome to another tutorial. In this tutorial, I'm going to continue our discussion on numerical integration with the Simpson's method. And we said that in Simpson's method, we just interpolate the function with a quadratic polynomial, and then in each interval, small interval, we, instead of integrating the function, we integrate the quadratic polynomial, which we know very well how to exactly calculate that, and it eventually gives us this result, right? And the question is, how do we actually find this integrating polynomial, or the approximation, this quadratic polynomial in each subinterval? Typically what we do, we use a Lagrange interpolating polynomial, and we briefly discussed this Lagrange method when I was talking about root finding algorithms using Brent's method, because the idea was the same there. We had to do a quadratic interpolation and find the root of that interpolating polynomial. So the way we write down the Lagrange interpolating polynomial is that, first of all, this interpolating polynomial is unique. And you can easily prove that the uniqueness of this polynomial that interpolates the function is unique. So for a quadratic polynomial, we need 3 terms to be able to uniquely interpolate the function. And then the way we write it down is like this. It has for here we have 3 points, right? A f of a, b f of b, and m f of m, which m is the midpoint. And then we know that at A, the polynomial should also go through f of A. At B, the polynomial should return f of B. At M, it should return f of M. So we write this down. We say that, okay, P of X must give me f of A, f of M, and f of B. And then I multiply each of these terms by a second degree polynomial. And that polynomial should return 1 whenever I plug in A. So x minus m, x minus b multiplied by f of a, but then I plug a into x and divide this polynomial by the result. So x minus m, x minus b divided by a minus m, a minus b times f of a. So if I want to find the coefficient of f of m, I take the 2 other points, a and b, and write down a quadratic polynomial, x minus a, x minus b times f of m, and then I plug m into this polynomial, m minus a, m minus b. So this whole polynomial returns 1 whenever I plug m inside. Now the key here is that whenever these 3 polynomials, these 3 quadratic polynomials are chosen, are written such that whenever you put, for example, in the first one, you put a here, the other 2 terms are 0 because they have x minus a. Similarly for m, so if I put m here, it returns 1 and the polynomial is f of m, but the other 2 terms are 0 because they have x minus m. Alright, so lastly, if I want to write the term for f of b, I multiply it by x minus a, x minus m, and then I plug back b in this polynomial and divide it by b minus a, b minus m. Alright, so this is how we write a Lagrange polynomial based on the values of the points and the values of the function at those points. Alright, so let's head to Eclipse and try to implement this Simpson's method. And we're not going to calculate the Lagrange polynomial first because we already know the result. So if in a small interval AB with a midpoint M, which is A plus B over 2, if you write down this polynomial, which looks a bit scary, but it's pretty simple, and then you plug it back here in the integral of A and B, and integrate term by term and find the exact result. The exact result is this, B minus A over 6, so the length of interval over 6 times f of a for f of m plus f of b. Alright, so in each subinterval we have this. And now if we have n partitions, if you sum this up over all the partitions, there is also a general rule, because some of the terms two neighboring intervals share some terms, right? So if I want to go from A to B and B to C, these two intervals share the point B, so f of B repeats itself, right? So I get B minus A over 6 f of A for f of M1 plus f of B plus the same thing f of B, and then I get a factor of 2 here. Okay? But for simplicity, we just find the value of the approximation in each subinterval and then sum it up. So let's head to Eclipse. In our demo integral project, we have integral 1D, and here I'm going to create public double Simpson, double start, double end, and int terms. And here again we are going to use a uniform partitioning, and we're going to calculate the values of the function, and eventually we're going to return the sum. But not only we need the values of the function, we also need the values of the midpoint, right? So let's create another array, func vals midpoint, new double. So if I have n subintervals, I have to calculate the midpoints n times. So here the length is terms, right? So the func vals are the values of the function, func vals midpoint at I, and then basically I'm going to evaluate the function value start plus I plus 0.5 times delta. All right. Now obviously we don't want to go out of the index, so we want to make sure that the I is less than terms. If I is less than terms, we do this, and that gives us okay. And then now that I have this, I will create another for loop, and in each interval I have my delta divided by 6 times func vals at the beginning plus so let's remove these two. I'm going to have 4 func vals midpoint at I plus func vals at I plus 1. All right. Okay. And this should be the Simpson's method, and again we're using a uniform partitioning. So let's go and test it. In test 4, we have this t times t squared, and we have the trapezoid, and now we're going to add Simpson. So result Simpson, and I'm going to call the Simpson method with 100 points. So let's see. And we can also let's just comment the errors. So we have forward, we have backward, we have center, we have trapezoid. The last one is Simpson. And as you can see, Simpson pretty much gives the exact result, and it should, because the function because it should give exact result for any quadratic function, and we are integrating a t squared, a polynomial, a quadratic function, so the Simpson should be exact. And let's go t cubed, for example, and the exact is n to the 4th power minus star to the 4th power divided by 4. So we have Simpson, pretty much exact result. Trapezoid and center are also good enough, the approximation are good, but Simpson is the order of magnitude for the error is way smaller or way better than the trapezoid and center, so it pretty much gives the exact result. So let's go T5 or T4, T cube or T4 for example. So I have to multiply this by end, start divided by 5. And again, as you can see, center and trapezoid, the accuracy is not good enough, but Simpson is pretty much accurate, 204.8000, so 7-8 digits of accuracy. All right. So that's the idea of Simpson, and but the next thing here is that if you recall, when we were looking at the root finding algorithm, I used recursive a lot in terms of solving the problem, and the general idea is that we can use recursion to also do integration. How do we do that? So basically the point of recursion is that whenever we can divide a problem into two smaller similar problems, then we can use recursion, right? And this recursion helps us to do implicit integration. And if you recall, I mentioned that the problem with recursion is that then the JVM, the Java Virtual Machine, creates a method stack, and it's a stack tree. We go each time we call a method at one step of recursion, we create a new stack, right? So we have a stack frame, and the stack frame keeps track of the calling methods, right? So when we have recursion, we go deeper and deeper into the stack, and then we have to come back up when we get to the stop criteria, stop condition. And the problem is that this going in deep into the stack frame and coming back may not be very efficient, may not be the most efficient way. But recursion is typically typically much simpler to implement when compared to a direct approach. And then the idea of recursion or recursively calculating an integration is based on the breakpoint rule. So if I want to calculate integral of f of x from a to b, I can choose a point inside the interval and then go from a to c and c to b. So I can divide one problem into two smaller problems, okay? So the stop condition is that, again, we can use any of the methods that we chose so far. One is, for example, I can set the stop condition is that when the interval is very small, I can approximate the integral by a constant value, which is the value of the function at midpoint times the length of the interval. Or I can approximate the integral with a linear approximation, which ends up being the trapezoid method, or I can choose the quadratic approximation, which ends up being the Simpson method. All right. So I'm going to show you how to do this in Java. So let's head to Eclipse and try to do the recursively calculating the integral. So public double forward rectangle recursive double start double end, but I'm not going to specify the number of terms. We can do that. We can basically do that as well, but let's set the stop criteria to something else. So what are we going to do? Let's do this. Basically we don't need any of these, so what we need is a stop condition and then the return condition. And in the return, I'm going to choose the, let's call the midpoint, double mid. Point is basically start plus end times half. all right, and then we're going to return okay, maybe we put this here, return we are going to break it down into two smaller intervals. So forward rectangle recursive start midpoint plus forward recursive midpoint times end from to end, right? So we are breaking the integral into two smaller breaking into two smaller integrals. And the stop condition here is that if let's say math.abs end minus start is less than 1 e negative 9, for example, what we are going to do is we're going to return actually there's no point in calling it forward, right? We could call it forward, and then here we do the forward approximation func.value at the start. This is the forward approximation. Okay, now let's head to the test integral class and let's see if this works. Result forward recursive. I'm going to call the forward recursive, but we don't have any integer number of steps. And then let's call this here. All right, let's run test 4. As you can see, it's still running to do the recursion, and that's not good because it takes a lot of time to do the recursion. Let's maybe let's reduce this to 1 e negative 4. And okay, so what we forgot here is to multiply it by basically the delta x, right, times end minus start. Okay, so the recursion is stopped, and the forward approximation was 199.714. The forward recursive is 204.79 which is much closer to 204.8, and that's because here we specified the number of terms, but we didn't have any idea of how the error changes with this. But here for the recursive we set the absolute error, so we are confident that we should be at least 4 digits of accuracy. Let's set it to E5. Now we should have 5 digits of accuracy, right? And we can go E6, for example. $799, this is 6 digits of accuracy, okay, and still fast enough. Now similarly we can implement the backward approximation recursively, so backward. And again, so the good thing about recursion is that you really don't need to do anything. You just break it into 2 smaller problems and call the same method. The downside is the fact that it's most likely not less efficient than if you actually implement the direct approximation, okay? So in the backward recursion, we just evaluate the function at the endpoint, and we call the backward recursion method. All right. So result forward recursion, and then we have result backward recursion, forward, backward. Let's update these with backward and run it. Now in this case they both have the same accuracy, 6 digits of accuracy. All right, and let's do the center approximation. So backward, center, rectangle, recursive. Here we do the evaluate the function at the center, point times so actually I can put this the midpoint in the beginning, and then I just evaluate the function at the midpoint. All right, times end minus start. So here let's do the center recursive, result center recursive, backward we're going with center. Okay, and then result center recursive. Okay, let's run it. It's not that much different from the backward approximate. Okay, that's because I forgot to update this with the center. Yeah, so remember, when we're doing the forward recursive, we have to call the forward recursive. When we're doing the backward, we have to call the backward. When we're doing the center, we should call the center recursive. And now we have almost the exact result. So the accuracy of the center recursive is pretty good, but I guess because the order of magnitude error is less, maybe we can just reduce the number of iterations. Yeah, it's still pretty good. 204, 799. Now the problem here is that the absolute error is typically not a good idea to implement, so we can also add some relative errors. So math.abs of end minus start divided by math. Let me just less than 1 e negative 5, or now if the end value is 0, we can also do a start, right? So we also look at the relative error, and it still works. Okay, so forward recursive, backward recursive, and again it's better to have these relative errors as the stop criteria as well. Forward, backward, and then the stop. So we can increase this. Let's set this to 7. So I'm just increasing the relative error to make it more accurate. Okay, and now let's go to do the trapezoid, public double trapezoid recursive, double start, double end. And actually we could here give the double error tolerance. All right, we could specify that here, and then the same thing here. So we have the midpoint, and then our stop condition here is that let's set these to tolerance. So the idea is that you can actually let the user choose the tolerance, or we can just set it. It's better not to hard code the tolerance here and have the user. So for example, But for now, just for simplicity, I'm hard coding the absolute error and the relative errors. But it's better to have them as argument. Absolute tolerance and relative tolerance for the interval. Okay. Alright, so in the trapezoid, we find the value of the function at the start point plus value of the function at the end point and divided by 2 times the length of the interval. So when our interval is small enough, so we just return this value. Okay? So it doesn't have a forward or backward or anything. We just take the average. The trapezoid just one interval and it automatically expands itself on the entire interval because of the recursion. All right. So let's go here and then do the trapezoid recursion. Trapezoid recursive. Boom. Here, here, and here is trapezoid recursive. Start, end. Let's run this. Each gives the pretty much exact result. All right. And we see that the center result and the trapezoid results are pretty much the same accuracy, which is pretty good, and they're very close to the exact result. And let's try to change the function to something more interesting. Let's say math.sin of t. As you can see, the direct integration is, we can really see that the direct integration is faster than the recursion, right? And but what we see that is Simpson returns 1.857779 for direct integration. The rest forward and backward, they're way off from Simpson. Center is 1.85799, so 3 digits, 3 decimal places accuracy. And trapezoid is 1.8573, and all of these because for 100 subintervals, right? Now instead of having the number of subintervals, if we go with the recursion and the absolute error, then what we get is 1.8577. So we have this accuracy very similar to Simpson's method. The backward is the same. The center recursive is also the same. 198,199. So this gives the trapezoid recursive gives almost exactly the same result as Simpson. But again, Simpson with just 100 subintervals is pretty fast. So it's better. The recommendation here is to use Simpson direct integration. It's very simple. It doesn't have any overhead due to the recursion and calling methods or going into the stack method. And let's finally go and implement Simpson recursion. So public double Simpson recursive double start double end, and again the same situation here. We have the midpoint, and if the stop criteria is not met, we go with the call the same method on the start to midpoint and midpoint to end. And when the stop criteria is met, basically what we are going to do is we are going to apply the Simpson's rule in the interval. So the Simpson's rule is n minus start over 6 times the value of the function at the start, the value of the function at end, 4 times the value of the function at the midpoint. Alright, so this is Simpson. And let's also add the Simpson here. Recursive, trapezoid recursive, Simpson recursive, and Simpson approximation non-recursive is 1.857777199. The recursive Simpson is 1.85777. So again, pretty accurate, 1988. And let's also do a benchmarking on which one of these two is more faster. So we're going to call test 5. And in the benchmarking, I just try to find a so let's find the time that it takes to evaluate the integrals. So we're using 100 subintervals here, and I'm going to use the timer method from the from my mathlib library. So I'm going to add a dependency on the mathlib, and then here I'm going to call timer. Actually we need to import it from mathutil. Timer1, new timer, and timer1 start, and then after ending this timer1 stop and timer1 dot show. Okay, and then the same thing here for the recursive. I'm going to use timer2, create timer2 start, and after doing the calculation, stop timer2, show timer2. So the Simpson duration was pretty much nothing. So it was quite fast with 100 subintervals, and it gives us very good accuracy. But the recursion, as I mentioned, takes time because of going into the method stack and recursive calling of methods. Let's increase this to 500 points, 500 subintervals. Pretty much doesn't take any time. So my recommendation is to avoid recursive implementations and always try to do direct implementation for numerical integration. Even if let's see what happens if I increase to 5,000, 2 milliseconds, pretty fast. Let's put this in the beginning. As you can see, the order of execution doesn't really matter. The direct Simpson is still very fast, extremely fast, doesn't take much time, and it gives us very accurate result. So avoid recursion whenever you can for numerical integration. Okay, thank you for watching, and I'll see you in the next video.